In our model of perfect competition, we assume that there's competition, lots of buyers, lots of sellers. We assume that there's no externalities, and we assume that we have perfect information, that all parties in the transaction are perfectly informed about the costs and the benefits of their actions. Obviously, these things don't always happen in the real world. So in this section, we've explored what happens when firms in particular have market power. We've explored how externalities and public goods lead to market failure. And the last thing we'll talk about now is what happens when people don't have perfect information. In life, many times we make choices when we don't know the outcome of our decisions. And that's what we're going to talk about today. How do we make choices when the outcome of that choice is unknown? Well, we're going to deal with specific situations in which we can at least guess at the probability of different potential outcomes. Of course, in real life, there are many unknowns that we can't even guess at, but here we'll at least begin to think about making decisions in conditions of uncertainty by assuming that we have some sense of the outcomes and their probabilities. So in economics, we tend to use the word lottery to refer to any situation where the outcome is uncertain, where we don't know exactly what's going to happen. We try to, in these situations, define all of the potential outcomes and their associated probabilities. Again, that may be difficult in real life, but you could at least guess at them. So let's start with our first example of a lottery here. And in this situation, we have a person who has invested or has the option to invest $100. And there are three potential outcomes. That investment can increase in value by 20%, it can remain the same, or it could decrease by 20%. So we want to start to learn how to characterize this lottery, this situation. And to do that, we want to think about the expected outcome. If you were to invest that same $100 over and over and over again, what would be the average return on that investment? So our expected value, you'll remember from statistics, is the sum of all of the individual probabilities. Okay, so here we have probability of outcome I times the payoff of outcome I. So in this particular lottery, the expected value would be 30% chance that we get $120 plus 40% chance our investment yields no payoff, plus a 30% chance that the investment declines in value. And if we add all of that up, we can see that the expected value of the investment is $100. So there's no return here in expectation for this investment. Now, would you make this investment? Would you give up $100 with certainty for a small probability of getting 120, considering that the expected value was $100? Your answer to that question might be different than someone else's. And one thing we'll explore in this section is preference for risk. Before we get there, we want to do one more thing to characterize this lottery. know the expected value is $100, but we also want to think about the range of potential outcomes. And we do that by calculating the variance of the lottery. So just like in statistics, we'll calculate the variance by taking the sum for each outcome, the probability of that outcome, times the difference between the outcome's payoff and the expected value of the lottery, the average outcome. And then we'll square that, of course, because some of them will be positive and some of them will be negative. And we want a measure of how from the average. Okay, so that gives us a sense of how wide the distribution of outcomes is relative to the average outcome. So here in this example, we would have 0.3 times 120 minus 100 plus 0.4, squared, plus 0.4 times 100 minus 100, that's going to be 0, plus 0.3 times 80, this is squared, 80 minus 100 squared. They're all squared, right? Because you can see that the first term here is going to be positive. And then the last term is going to be negative. But when we square it, then we're adding together sort of the real distance. We don't want them to cancel out. If we have one really good outcome and one really bad outcome, it doesn't mean that there's no dispersion, right? It means there's wide dispersion. And so we want to add those together. And that's why we're squaring them. So everything is positive. Okay, so then here, we're going to get 0.3 times, this is 20 squared, which is 400, plus 0.4 times 0 plus 0.3 again times 400. So you can see, right, even though 120 is bigger than 100 and 80 is smaller than 100, they're the same distance from 100, so they give us the same term in that variance calculation. Okay, so then if you plug that into your calculator, that's going to give you 240 for your variance. Okay, so this is, again, a measure of how wide the distribution of outcomes is. And that's going to depend both on the probability of outcomes that are far from the distribution and how far they are from the distribution. Okay, so let's compare this first lottery then to another investment where we can invest $100. And you'll notice that the potential payoffs here are the same, but the difference is the probability of those payoffs. So here we have $120 with a probability of 10%, $100 with a probability of 80%, and $80 with a probability of 10%. So if we calculate the expected value, we've got 12 plus 80 plus 8, which again gives us an expected value of 100. Okay, so it has the same expected value of the other lottery. If we were to repeat this investment over and over and over again, on average, we would end up with $100. But the variance is going to be different. The variance is different because you can see that the probability of outcomes that are away from the mean or the expected value is lower. So this lottery will have a lower variance than the previous lottery. Okay, so if we have 0.1 times 120 minus 100 plus 0.8 times 100 minus 100. I keep forgetting these squareds. I'm so sorry. Plus 0.1 times 80 minus 100 squared. Then what we end up with is 0.1 times 400. I'll write that out. Plus 0.8 times 0 plus 0.1 times 400, and we get 80, right? 40 plus 40. So you can, again, see these lotteries have the same expected value, but a different variance because the probability of outcomes far from the mean is lower in the second lottery. So the variance is determined both by how far the outcomes are away from the mean, and also by how likely those far away outcomes are. And this is the way that we think about risk in economics. So we are going to define risk as related specifically to the variance of the lottery. So if the lottery has a larger variance, then we would say that that lottery is riskier. The outcomes are more uncertain than a lottery with lower variance. So here, the lottery in 1A, right, is riskier than the lottery in 1B in that the outcomes far from the mean have a higher probability of occurring. So there's more uncertainty in the actual outcome of that investment.